Okay. So in my mind, we are done units 5, 6, 7, and 8. That doesn't mean that I won't answer questions, but that means that I think I've covered the main material. Maybe I'll ask myself I'll see if you have any questions, and I'll ask myself some questions. That's the material for the second test, 5, 6, 7, 8. And that will be, I always do a 9, try to get you time to finish the labs associated with 5, 6, 7, and 8 before we have the test. So the test is going to be after Easter. So here I have brought up a calendar. So you may ask questions today, or maybe we will start talking about new material. Same thing on the 31st. Then we're off the 5th. And I don't want the test to be in that week when we can't be in the room. The software works better in the room, so it's an advantage to the people who actually want to be in a room with me, and I want them to have that advantage. That should be some advantage to being in a room with me. And so the possible dates for a test then are 12 and 14 for test 2. And so I'm asking at this stage again, is there any major exam you know of on those days that I should try to avoid? Okay, I'm not hearing anything from anybody, so then I'll just make up my mind what I want to do. And I have another tests in my other class as well. So I'll keep my test away from my test, but I haven't heard anything about Redmond tests or McCooey tests or the Hiley tests. Long. I think I did hear something about mystery, and I thought I heard that he was trying to get his in before Easter because he's smarter than me. Okay. So that's where things stand test wise. Before I ask questions of myself, do you have any questions from these units? Yes. Multiplication. Okay. Yeah, I don't think I ever have, so that's a good one. So that was part of shifting, right? And so where was that? Here? I don't know. No, that was already in floats. That's maybe it was B. Okay. Okay, so it's this, and I will do one like it. I'm not enabled editing, so I can't copy. I'm going to take one of these. Control C, and then I'll put it down below. Control V. Now let's imagine first, so I'm not doing your work, I'm doing, let me put on a page break. Okay. Let's first imagine something simpler and think of just a decimal problem, 1, 2, 3, and we'll multiply it by, I don't know, 3, 2, 1, try to keep the number small. And then I don't need one of these rows, okay. So delete cells in an entire row, okay. So if I had this problem, at least the way that, I was taught, I think you might have been taught like 8 ways to multiply. I was only taught 1. And so you take the number, the first number, and you multiply it by this. So 1, 2, 3 times 1 is 1, 2, 3. And then I'm going to take that first number, 1, 2, 3, and multiply it by 2. But it starts here and goes over. And so that's what, 2, 4, 6. And then I'm going to multiply that first number, 1, 2, 3, by 3, and it goes here. So 3, 6, 9, like that. And then you start adding your columns. So this would be 3. This would be 8. This would be 4, carry a 1. I don't know if I want to show the 1. Maybe I'll show and so that's 9, and then a 3 or something. That's a 9, and then that's a 3, and then always probably a good idea to check. But I'm looking for the work, so you just can't check and tell me the answer. I'm not interested in the answer. I'm interested in the process and the thinking. And so calc, but it is a good idea to check. So 1, 2, 3 times 3, 2, 1 is 39483. I got it right. Okay. So that's the way I'm thinking of multiplication of decimals, in that you do this, you multiply the number, and when you're multiplying by the tens place, the lowest digit's in the tens place, and when you're multiplying by the hundreds place, the lowest digit is in the hundreds place. And so I want to do the same sort of a thing, but with binary. And so all I have is 1s and 0s. So I'm either multiplying by 1 or multiplying by 0. And let me change, I don't know, I'll change this and that and that, and maybe this, I don't know. We'll see. Okay. So I take the top number and I multiply it by 0. So that's 0s. And then I take the top number and I multiply it by this, but I'm multiplying by 1. So it's just the number. And here's the point. The number is shifted. And that's what we are talking about. That's one of our main themes for this unit 7 was shift registers. And so then I multiply by this one. And so I put in the number, it's another 1. So it's 1, 0, 1, 0. And then the final one is 1, 0, 1, 0 again. 1, 0, 1, and 0. And then I'm left. So now we are multiplication of integers is shifting, which we know how to do, and adding, which we know how to do. So in the strictest sense, if we, throw together the logic, we can throw together our shifting logic and our adding logic, and we can then have multiplication. So in principle, we can build circuitry that gives us integer multiplication. So now I'm left to do the adding. So that's 0. So that's an, oh, that's not a 0. That's a 0. That's a 0. That's a 1. That's a 1. That's a 0 with a carried 1. And you don't have to show the carries, but you can if it helps you. That's a 0, carry a 1. That's a 0, carry a 1. And so then that's a 1. And let's test it on the calculator. And so I should go over to programmer. And what am I trying to, and in binary, and then try 1010 times 1110 and I get 1,000,1100. So again, part of the reason we'd like to get it right, but also I need to see this intermediate stuff, specifically the shifting. That's the whole purpose of this. So that is the game. Do the shifting. If you if that position was a 0, then you multiply by 0, which gives you 0. If it was a 1, then you give me the number, and then you do the addition. And you can fake it and do the shifting, and then do it on the calculator and pretend you do the adding. That's fine by me. I don't care. How would I know? But I need to see this filled in. The carrying ones are up to you whether you show them or not. Any other questions you have for me? That wasn't one of the ones that I was going to ask myself, so it's good that you asked. Anything else you want to ask me? Okay, we're coming down then to the questions where I'm going to ask myself. I'm going to ask myself, the one thing that I keep trying to get you to ask is the one type of floating number that I haven't done. And then the other thing I'm going to ask myself is the thing, oh, somebody's chatting with me. How does a diode work? Okay. I will talk about that. We'll talk about that. Okay. Let me do what you asked, and then I'll do. So let's do multi-sim. And I'll build some quick little circuit. So there is the diode. And I'm just going to do a simple little virtual diode. Maybe I'll get a real diode. I don't know. Let me pick one. So I pick some diode. I want some resistor. I'm just going to make a very simple circuit. I want some resistor. Yeah, 215. Why not? That's fun. I'm going to, I don't want that. I'm going to rotate this, rotate, not the label, but rotate the whole thing. I'm going to have a battery. I have a ground. I'm going to get a voltmeter, which will go in parallel with the diode. And let me get an ammeter in here as well. I'll do vertical ammeter like this. Okay, so I have a simple circuit that is a battery and a battery, a diode, a resistor, a volt, and an amp. This is going to give me what we call the IV characteristics, the current and voltage characteristics. And let me start with something pretty small. 1/10 of a volt. And when I turn this on, I get some voltage across some current and some voltage. Okay, and so then I would write that down, and then I'm going to keep changing this. So so I did 1/10 of a volt, that's a small voltage. And let me change this property, which, yeah, it goes for like 1/2 of a volt now. And now we see that this gets about 0.148 of a volt. So before it was getting about maybe 1/2, now it's getting much less than 1/2. Let me take this guy up even farther, maybe to 2 volts. Okay. And you see that in the beginning, the diode took a lot of the voltage, and then it takes once it gets going, it only uses up a small amount of the voltage. That's typical of a diode. Now, I chose a different diode from my list than I think what I asked you to do, but that is a general property of diodes, that they, in the beginning, so if these were 2 resistors, let's compare ourselves to if there were 2 resistors in series, then the proportion of what each resistor would take would be the same. But this proportion now is, again, when I had 1/10 of a volt, it took almost half of it, more than half of it. And now that I'm up to 2 volts, it's taking more like 1/10 of the voltage. So the ratio of the voltages is not the voltage used by the diode to the total voltage is not the same. And if these were 2 resistors in series, it would be. So the effective resistance of the diode is changing. So in the beginning, the diode's like a big resistor, or at least as big as this guy. And now that we've got some current going, he acts like a much smaller resistor. And that's going to be a kind of on-off kind of property of diodes. So that's one property of diodes, is they're sort of a kind of on-off. So we talk about them that we think of this arrow as being the direction. One of the main properties of a diode is the direction. And so the current can flow in this direction. But another property of a diode, it tends to be, a transistor is going to be even more so, but a diode's enough to be sort of, it's nonlinear, and you can treat it to some extent like an on-off kind of a device, that once in the beginning, it has a large resistance and it's kind of effectively off, and then it gets going and doesn't take much voltage, and then you can think of it more as on. So we're going to treat them as something that provides us with direction in a circuit, but also something that has an on-off feature. So in lab 8, I think we are focusing on their direction properties. Well, I have you do the characteristics, and you'll see I ask you to find the resistance. The voltage over the current is the resistance. So I ask you to find the resistance of the diode, and that will change. And you'll note that that was different than we saw way back when in lab 1, when we just had a resistor. So is that here? So I was just talking about that circuit I built, something like this. And so you change this voltage and then you get this voltage and this current. Be careful of the unit. Sometimes the unit, if there's a very small current, it may, instead of giving you milliamps, it might give you a little U for microamps. And so if this told me then it was, let's say 1.2 microamps, then, but I'm asking for you to give me the answer in milliamps, then you owe me 3 decimal places. So if, where do I want to put that? Let me enable editing. So I'm just making it up. If this said then it was 1.2 UA, if that's what the ammeter read, then I've asked you to fill in this table in milliamps. And so that means you owe me 3 decimal places. And so that's 0.001. So I moved the decimal place 3 times to go from micro to milli. I think the voltages will always be volts. I don't think we have a worry there, but you have to watch the units in this thing. And then resistance, I just told you, is voltage divided by current. If volts divided by milliamps, we've done this, we've played this game before, that's going to give you kiloohms. And what you should observe here is that it changes, that the resistance started off quite high and then comes down. And then we'll ultimately, for now, we're just going to say, oh, that's non-ohmic, that's not linear. But ultimately, we'll start to move towards where we say that it was off and then it was on. That's where we ultimately want to go. But before we get to thinking of diodes as logical things, as on and off, we focus in this lab on their direction thing. Okay. So in this circuit here, this is a signal generator. That's one of these, turn this guy off. That's one of these things over here, or maybe they're calling it a function generator. The function generator. And this thing gives AC. When we have a battery, that's DC. So that's all of the voltage. The voltage we think of as pushing. Everything's pushing in one direction. When we bring in this function generator, the direction of the push varies in time. So it's alternating. We call it AC, alternating current. So and then it has different properties. You can say the amplitude is how high is it going to go? Is it going to go up to 10 volts? The frequency is how fast does it? We're not going to worry too much about the frequency in the beginning. We'll worry about frequency later in the course. But so we're going to play with the amplitude. Okay. So if I had here, instead of this battery with its one direction, if I put in there instead a function generator, then I would see that there were times I was pushing the current in the way it would go. And there's sometimes I'm pushing the current in the way it doesn't want to go. And if you try to push it in the way it doesn't want to go, it sort of gets cut off. So let's just, as I'm talking about that, try this. Let's put this in here. Let's put this over here. And then let's make that like down here. Okay. And then this is now time dependent. So I want to look at if I want to do a time dependent thing, I replace a voltmeter, as you all know, with an an oscilloscope. And I like the 4-channel one. So now I'm going to look at what does the voltage across the diode look like? And then maybe I'll look at another time the voltage across the resistor. Okay, so let's turn this on. And I don't have the oscilloscope up, so I don't see anything. And let me turn it on again. Okay, and what are we getting? I'm going to change my time scale. Okay, and what I was trying to put in, what this puts in is a sine wave. And what I'm getting out here is only parts of a sine wave. It's cutting off some parts and leaving some other parts. And that's because of the directionality of the diode. Okay, so those are the things I'm asking you in this lab 8. Here I'm asking you to work through the IV characteristics, see that the resistance changes, then it's not constant. When we did this game before, way back in lab 1, this number kept staying the same. Now it's like 2.7, 2.7, 2.7, 2.69. Here it's going to change radically. It's going to be like, 3,000, and then it's going to be 100, then it's going to be 6, and then it's going to be 0.25 or something. It's going to change a lot. Okay, then we're interested in the direction. So I just put the voltmeter across the diode. You are putting it across the resistor. So your picture is going to be different, but the overall explanation will be the same. The diode stops it from flowing in one direction and allows it to flow in the other. And so you'll get, instead of getting a full sine wave, it's going to be cut off. God damn it, use your voice. Resistance across the diode is voltage divided by current. That is correct. So resistance is voltage divided by current, and it is, if you do what I asked you to do, put everything in milliamps, it'll be volts divided by milliamps, and that's going to give you kiloohms. Okay. And this one, you have a voltage coming out, and it comes to this junction, and it has 2 choices. It can go in this direction or that direction. If I'm talking about a positive current, it's going to go in this direction. That's the direction diodes allow. It's not going to go in that direction. So you find a way, you find a path. When the path is positive, you start at the plus. So you want to start here and end there. When you're in the, where's my little stupid snipping tool? What I'm inputting looks like this, ups and downs, sine wave. When I'm in the positive part, that means I'm going to start at the plus and end at the minus. So let me draw this stupid little thing. So here is my signal generator with the plus and the middle and the end. And so when I'm in the top part, I'm going to start here and end there. And then in my other part of the circuit, what color is my custom? It's green, okay. So in this part, I'm going to start here and end here. So you have to find some path You have to find me two paths. You have to find me a path when we're positive and a path when we're negative. So you have to find me this red path, you have to find me the green path. The red path starts at the plus and ends at the little node in between, the ground, I'll call it. And so you've got to find your way through these diodes and this resistor. This guy's just the oscilloscope's just an observer. So you find a path from the plus through the diodes, through the resistor that gets you here. And then you have to find me a second path, a green path, that starts in the middle and goes through the direction and goes through the diodes and the resistor. You can only go through the diodes in the direction the arrow points. And then you find me a path that goes from the plus to the middle, and then that's the red path. And then you find me the green path. You find me the path that starts in the middle and goes and ends on the plus, and only goes through the diodes in the direction that the arrow points in. Any other questions? That was a good question. Wish it were spoken instead of written, but beggars can't be choosers. Any other questions? All right. So what else do I want to say? I want to talk about 6, the thing that lots of people seem to be getting wrong in 6. And 6B, I think. Yeah. Is it? Yeah, this adder with resistor. Now, did I? Yeah, there it is. Adder with resistor start. So I give you this head start. Now, some people did the lab before I gave the head start, and they made their own registers, and that I was fine with that. But okay, if you're using what I gave you, then you've got to figure out we're adding 4-bit numbers. We've got to figure out who's the 1's place, the 2's place, the 4's place, the 8's place, because we want to display the numbers correctly. And here in the middle is the adder. And the adder determines things because you carry. You see how the carry's going. This is the 1's place, the 1's place carrying over to the 2's place. This is the 2's place carrying over to the 4. This is the 4 carrying over to the 8. So I'm not going to build this for you. I'm going to sort of copy it and then do some scribbling. So just based on the carries, we know that this is the 1's place, this is the 2's place, this is the 4's place, this is the 8's place. So now I want to display it. I'm going to call this middle one the sum. I'm going to call this A and this B. And when I'm displaying, this is the 8's place and this is the 1's place. So the sum, if I'm displaying the sum, I connect the 8's place to the 8's place of the display, the 4's place to the 4's place of the display. I should do the same for the 2 and the 1, but I'm lazy. Okay. So now up here in register A, what happens? Here's the register that feeds into the adder, then tells me it's the 8's place. So this is also the 8's place. And so if I want to display what's in register A, this is the 8's place of what's in A, so I connect that there. And this is the 4's place, so I connect it there. And then the same thing for B. This is the 8's place of B, so I connect it to the 8's place of the display. This is the 4's place of B. I connect it to the 4's place of the display. You can't just sort of connect things to other things without thinking about it. The display, we're displaying numbers. Our whole number system is based on positional weighting of having a 1's place, a 2's place, a 4's place, an 8's place. And so you got to know when you're displaying, where's your 1's place, where's your 2's place, where's your 4's place, where's your 8's place. And that was determined for us in this circuit by the adding. The adding carried in a certain direction. That told us the relative, the positional place of each of these of the circuit elements. Then you have one. Now here's what the people who were too fast for me. Here's the one point that they may have missed. Some of them went back and did it, which is also fine. I only have one set of data switches. So I need to get data into register A and data into register B, but I only have one set of data switches. And so, but I have 2 clock switches. So if I prepare the data, and if I go through the clock, the A clock, that puts it in A. Remember, I have to go through an edge. And if I prepare my data and go through a B cycle, that puts it in B. So prepare a number. So this 0 over here is going over here. So this is again, the 1's place, the 2's place, the 4's place, and the 8's place. And so you prepare the number. I tell you I want a 7. You go to the calculator, you put in 7, you say, oh, that's 0, 1, 1, 1. And so I make it a low, high, high, high. And then I wanted that in register A. So I go through a clock cycle for A. But a lot of people are getting these wires backwards. Okay. What other question am I going to ask myself? Anything on this before I think I'm the one who asked the question, and I think I've answered my question, but do you have any questions? All right. So the other thing that I keep hinting that I want to show you, and nobody's asked me, is how to do the floating point number when the magnitude of the number is less than 1. So let me just pull up something like one of those. So that was in, I think it's in 7 and in 8. I think it's in the end of 7 and the beginning of 8. Let me do 7. And I'll change the number. And again, this, like the multiplication, you've got to show the work if you want all the points. So I'm going to copy this. I'm going to insert a page break down here. I'm going to paste. I'm going to change the number to what? Give me one more 0 and there. 000044. That sounds like a good number. Okay. So it says to me, multiply that by 2 to the 24. So that is a scientific mode thing. 0.00044 times 2 raised to the 24. And there I have my number. And I only want to keep the whole number, 738. And then I'm going to put that into programmer mode, 738. And that is giving me here, and I'm using 10 places. I'm expecting, I wanted 24, I used up 10, so I'm missing 14. Okay, so now I'm going to repeat the above, but with 24 plus 14. So let me go back to programmer, not to programmer, back to scientific. Okay. Point, what was it? 0.000044 times 2 raised to the parentheses 24 plus 14 close parentheses equals. Okay, now I have some whopping big mess. Control copy. So now I'm going to do that. Control V. So I'm going to say that was 0.000044 times 2 raised to the 24 plus 14. And that gave me that. And I'm going to truncate it. Some people will round, I truncate. So if our answers are different by the last bit, I probably am okay with that. And now I'm going to copy that, Control C. I'm going to go to back to programmer mode. I'm in decimal. I'm going to Control V. And there's the number I'm putting in. And here's my binary. And it gives me 24 places this time. All right. Okay, so now it's grouped in fours. 1, 2, 3, 4, 5, 6. 6 groups of 4. That's 24. Okay. And what did I have? I want now the dot to be so before the dot was here 0 1 0 1 1 1 0 0 0 1 0. Okay, so the original dot was no, I want to originally I wanted 24, so it was originally 0.123 4. Okay, so that is the game. Then I want, so that I wanted to be a 1 and then 23 places, but it didn't get them all. So now I need this to be not only am I missing 14 places, so I have like 14 zeros in front here that I'm missing, but I want to get the dot also here. So the number at this stage that I'm thinking of is like 14 leading zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then this number you don't have to write out. You have to write out some of this stuff, but not all the stuff I'm doing right now. So right now we're thinking of it as like this, dot, blah, blah, blah. Okay. So, but I want to move this dot so that it's here. So I want to move it past the 14 zeros and one more. So my shifting is a 15, but it's a minus 15. I have to shift. My rule is to have 1 and then a dot. But what I have is a dot, then 14 zeros, then a 1. So if I want to move my dot so that it's after that first 1, I have to move it 14 to get it past all those zeros, and 1 more to get it past that original 1. So that's 15. I'm making the number, by moving the dot, I'm making the mantissa bigger. So I've got to make the power negative to keep the number really the number I want. And then, but I have this bias gain. So it's the 15 that corresponds to my shifting. And then a bias of 127. So let's go to here in decimal and clear, and 127 minus 15, and that is 112. And that is here. Now the exponent has 8 and this is 7, so I'm going to throw a 0. So it was a positive number, so 0. The exponent was 0, 1, 1, 1, 0, 0, 0, 0. And then the mantissa is here, but remember we store the mantissa, we don't store this 1. So I'm going to put that 1 in red and make it 24 point. That's the one that's I'm not going to store. So it's going to be 0, 1, 1, and then 1, 0, 0, 0, and then another 1, 0, 0, 0, and then a 1, 1, 0, 0, and then a 1, 0, 1, 0, and a 0, 0, 1, 1. Okay. And let's see what Herr Schmidt has to say. There are other converters. If you like other converters, you can use them. But again, don't forget the I need intermediate steps or you're going to lose points. So what was my answer? My answer was, I want that. I want this. There we go. I want for the exponent 0, 1, 1, 1, 0, 0, 0, 0. For the mantissa, I want 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1. Okay. And so this says that it's 4.399999 something something times 10 to the minus 5th, which is 0.000044, which is, so it's not exactly the same. It's never going to be. It's there's always some rounding in floats, which is why I took some points off of my programming students who wrote me an if statement that had like, if the price is this, and then they said, if the price equal something, and I never ask about equality of floats because they're never what you think they are. They're only very special numbers that you can write exactly. All right, so those were the two questions. The adder with registers, I wanted to ask that to myself. This floating point where the number was, the absolute value of the number was less than 1. I wanted to ask myself that, and I have. Somebody asked me about multiplying, which involved a shift. And so once you know what I want, it's usually very easy to get those points on the test. And somebody asked me about diodes. So we want in lab 8, we want to get their voltage current characteristics. And we also want to understand their directionality. And I'm being chatted at again. Where did I get the minus 15? Okay. So when I took my original, where am I at? Okay. So I took let me mold this down. I took the 0.000044 and I multiplied it by 2 raised to the 24. And the 24 is just cooked into my float, my standards for a float. We talk about either 24 or 23. Are we talking about the number? Or are we talking about what we store? So right now I'm talking about the number. Only at the end I'm going to talk about what I store. So I'm talking about 24. So I take my original number, I multiply it. I deal with it as a fraction. So normally I would say I would deal with the whole number and I would take away some of the bits, but there was no whole number. So I'm using all 24 to deal with my fraction. So that's where I came up with this 738, yada, yada, yada. I truncated. I have 738, and that gave me this number, and that used 10 places. So I was looking for 24 places. It only gave me 10. And so I'm missing 14. So, and so I think of it as dots, and then this is 14 zeros in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the number that I get, I have to think of as dot, 14 zeros, and then a 1. So this 1, this is the 1 over, this is the halves place, the 1 over 2 to the 1. This is 1 over 2 to the 2. So my first bit here is in the 1 over 2 to the 15, I believe. And so what is that? Let me be a scientist. 1 divided by 2 raised to the 15. And that's 0.00003 something. So that makes sense that I am bigger, the number I'm representing, which is 0.00004, is bigger than this. So I expect there to be a 1 in the 2 to the minus 15th place. But if I doubled this, it would be 0.00006. So 2 to the 14th place is too big. So I'm going to have a 0 there. So this makes sense. Then I got this. So that's what I'm thinking of now. I took my original fraction, I multiplied it by 2 to the 24. It gave me so many places. Do not put any zeros out here. We don't count them. Then I used up 10 of my 24, so I have 14 remaining. So I think of it as dot and then 14 zeros. Okay. Now you asked me about the 15. So my rule for floating point numbers is like my rule for scientific notation. It's some number that's not 0, dot. So when I move this dot to get myself in proper scientific notation or floating point representation, I have to move this dot. Not only do I have to move it past the 14 zeros, but I have to move it past this 1. That's my 15. The 14 zeros plus that 1. Then I'm making this number, if I'm moving this dot, I'm making this number bigger because I have the dot way out here and I'm moving the dot in this direction. So I'm making this number out front bigger, and I've got to compensate that by making the power of 2 negative. And I'm moving the dot 15 places. So it was 2 to the minus 15. That's the minus 15, then my bias of 127, because that's our way in the floating point standard of dealing with dealing with the numbers maybe positive or negative. Now I don't know if I have any time to do anything new, so I hope somebody will ask me a question, or maybe I'll have to ask myself another question. I don't like to throw 15 minutes away or 20 minutes away. All right. What can I do in 20 minutes? I can talk about the history, the hardware, and so let me give you that little blah lecture. Unless you want to ask me a question while I'm finding this. You do have a question. Oh, okay, sure. If I give you the float, sure. That will kill my time, so thank you. So that was here. What if I give you the floating point number? So what if I give you this? I'm gonna come down here, insert page break. And what if I did this? Okay, so I gave you a 1 the last time. Let me give you a 0. Changing this to a 1. And no, let's leave it 0. Now let's make it 1. 1 1 1 1 0 0 0 0. That should be easy to remember. And then what am I going to do here? 0 0 1 1 0 0 1 1 0. That'll be a nice pattern. Be easy to put in. Okay. So here's my number. The sign is 0. The exponent is 1 1 1 1 0 0 0 0, and the mantissa is 0 0 1 1 0 0 1 1 down for 23 bits because this is what's stored. Okay. So I'm going to, this is my overall what I'm doing. So I can say it's positive. Sometimes I write it like this, where it's -1 raised to the sign. So -1 raised to 0 is positive. Or you can just remember, which is what more often what I do is just say, oh, the number's positive. Okay. I need to get a number from my exponent. I need to get a number from my mantissa. Let's do the exponent first. I take my 1 1 1 1 0 0 0 0. I'm going to convert that and then unbias it. That's my term for it. I don't know if it's a real term. So I'm in binary. 1 1 1 1 0 0 0 0, and that is 240. And then I'm going to unbias it. So 240 minus 127 is 113. So that's my power of 2. So I'm going to put together these pieces. Some number times 2 raised to some number. And then it's plus or minus on the front, but I know it's plus. Okay, so now I know the number is that I'm raising it to is 113. Times 2 raised to the 113. Okay, now I need the number out in front. Okay, I need to remember what a mantissa is. Remember 1, then it's missing the 1. There's the 1 in the front that's not stored. I have to remember to bring that back. And then I have to remember what it means. It means there's this 1 in the beginning, and then there's this. Thanks for that. All right, I'll just have to type it. It's 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Let me do a little space thing just to help me count. 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1. That's 1, 2, 3, 4, 5. So I have too many. Okay. 1, 2, 3, 4, 5 groups of 4. That's 20, and then 3. All right. So that's, and then this was the implied one. So once again, let me make that red and 20-point font. Okay. So that's the one I brought back that wasn't stored. And so this is the this is what I'm thinking I have this. So if you wanted to grind out and say it's 1 and no halves and no quarters and there's an 1/8 and there's a 16th, you can do that. That's what it means. That's what we're going to get. I'm lazy. I love calculators. So what do I want to do? I want to move this 23 places and then divide by 2 to the 23. So I can take this, I'm just going to write it below. Without the dot went bye-bye. And then I made it a big number, and how, by moving it 23 places, and how do I compensate for that? I multiply by 2 to the minus 23, or I can say divide by 2 to the 23, which is the same thing. So do you want me to say multiply by 2 to the minus 23, or do you want me to say divide? You didn't answer fast enough. I'm going to say divide by 2 to the 23. Okay, so I'm going to take this number and put it in the calculator in binary mode. See if I got rid of that point. I thought I got rid of that point, but I didn't get rid of the point. So let me see if I can copy and paste this in. If not, there's a nice pattern, so I can just type it. Control C. I'm in binary mode. I'm going to paste Control V. There's my number. Does that make sense? Yes. And then I'm going to get that in decimal. And I'm going to divide that by 2 to the 23, which I'm going to do that over in scientific mode. Take that number. I have it. I think I have it saved. Move to scientific mode. Control V. Put the number back. Divide by 2 raised to the 23. I should get a number between 1 and 2. I do. Here's my number between, again, remember that one that wasn't stored but was there is 1. And then I have no halves and no quarters, and then I have an 1/8. So this number here is less than a half, less than a quarter, more than an 1/8. So it makes sense. And now I'm going to put my pieces together. Okay, so 1.199999 times 2 raised to the 113. And I can put that in the calculator. I can also Google it. Force Google to be a calculator. Let me take away the plus. That'll confuse it. Let me take away maybe this space. Maybe the other. That should be good. So there's the Google. I Googled what I wanted. Google will calculate for you. If it's clearly a calculation, Google just does the calculation. I don't want that. Probably want this. Okay. So putting all the pieces together, this is what I got. Control V, 1.246 times e to the plus 34. And then Herr-Schmidt. What does Herr-Schmidt say? So here's the original thing, and then refresh this page. Herr-Schmidt, it's 0, 1, 1, 1, 1, and then 0, 0, 1, 1, 0, 0, 1, 1. That's why I like the patterns. Makes this part easy. Okay, and so then their number is 1.246 e to the 34, which is times 10 to the 34, which is what Google told us. Somewhere I have it down there. Okay. So again, I need to see some of the intermediate work or you're not getting points. So I have to know that you understand it's almost 1.2. You know, if you don't keep a zillion digits, but you are in the right, you're in the ballpark, I'm going to say fine. So again, so on this test, when's this test? Not Wednesday, not the week after Easter. We have Monday off, so it's not this coming Wednesday, not the Wednesday after, but so not the 31st, not the 7th, but I think the 12th and the 14th are up for grabs. Nobody's told me that they have any major exams on those dates. Labs units 5, 6, 7, and 8. 5 is adder and subtractor. 6 threw in registers. 7 made those registers shift registers, which also brought up floating point numbers and multiplication and CRC. And then we talked about semiconductors. So there's some like vocabulary there in bands, understanding a little bit about bands and forward bias and reverse bias. And then there are some circuits with diodes. Anybody have any questions? Probably the thing I left most vague. I don't think I left too many things vague, but I sort of told you what I wanted here, but I didn't tell you the answer. Most of the other things, I pretty much told you the answers. And then I think I have a circuit with a diode clamp, which is very similar. Just you throw in a battery somewhere along the way. And the question is always, is the diode conducting or not conducting? When is there enough push to get the current to go through the diode? When the current's going through the diode, it behaves one way. When the current's not going through the diode, it behaves a different way. So it's directional, but it's also kind of, I remember, ultimately sort of almost an on-off device. So when it's conducting, it's sort of on and it behaves one way, and when it's not conducting, it's sort of off and behaves a different way. So you get parts of the circuit that look different. And the diode clamp is just another sort of thing on this about sort of saying, when is the current flowing and when is the current not flowing? Okay. I will leave it at that. I will let you ask me more questions on Wednesday. I don't think I will allow the whole period to be questions, but if you have questions at the beginning, I will certainly answer. Okay. I'm not missing any more chats. Okay. Let me stop recording. Or go back up there.